Hello, ladies and gentlemen. I'm Olzhas Kaiyrakhmet from UNIST in South Korea, and I'll be talking about my work titled SLM-DB Single Level Merge Key Value Store with Persistent Memory. Let me outline my talk. First, I'll go through the background and go over the contributions that we made. Next, I'll be talking details of our architecture. After that, I'll be evaluating our work, showing evaluation of our work, and finish up with a conclusion. So key value databases actually store some values and associate those values to some key. And the values can be a string, it can be a document, or it can be a picture. So that's why the key value stores or database are so popular to use. One of the famous approach to implement a key value store is using log-structured merge tree, which is introduced by O'Neill. It's very optimized for heavy write application usage, and it was designed initially for slow hard drives. It consists of key+1 components, and each components do batch merges from component to component. Component 0 does work as a in-memory buffer for the updates. And all the components are sorted. Disadvantages of the LSM-tree are as follows. So let's imagine if the applications issues a get operation. So first, it will try to retrieve the value from the first component, component 0, right? If it's not exists, it goes to the C1 component. And if it's not exists there, then it searches all to the components. And in the worst case, it can end up trying to search all the components in the LSM tree. So it's quite an overhead for it. And also, it does these batch merges from component to component and frequently overwriting the same data all over again. And that leads to the high disk write amplification. State-of-the-art LSM-tree implementation is Google's LevelDB. Well, here, mem table and immutable mem table works as a component 0 from the LSM tree. So all the updates go to the in-memory buffer, mem table, and that's implemented as a skip list data structure. But before inserting into the mem table, first it inserts to the write-ahead logging. Please note that by default, it does synchronize every write to the log. Therefore, if the crash occurs, some of the recent updates can be lost. So it doesn't have a full consistency. When the mem table gets full, it marks immutable and scheduled to be merged to the disk component. So it is called a flush, so it sequentially writes to the disk. And it's write to the disk as a sorted string table file. So when one of the, in the LevelDB, the disk components called levels. And if the level gets large, then it's scheduled to do a batch merge of one of the files to the next level. And that operation called compaction. Usually, each level is 10 times larger than the previous one. All of the file organization and the metadata about the files are stored in the manifest file. So there have been a lot of approaches to optimize an LSM tree, and we're interested in optimizing it for the hardware. And this hardware is, new hardware that's coming up is persistent memory. And pros of this new hardware is that it is byte-addressable, it is fast, and it can store data persistently. So the simple approach to adapt LSM tree for the persistent memory is that whether switch in-memory buffer to store it in the persistent memory, or just to store the disk components inside of the persistent memory. Well, our approach is quite different. First of all, we, of course, store our in-memory buffer in the persistent memory, and we have our only single component inside of the disk, and that's does a self-merging. So there's only single component there. And to navigate through the data that's stored in the single disk component, we have an index that is also stored in the persistent memory, and we use B+3 for indexing. So this is more detailed architecture of our work. So as well as in the LevelDB, we have a mem table and immutable mem table. So because they are stored in the persistent memory, we don't need actually any write-ahead logging. Well, when it gets full, it's marked immutable, scheduled to be flushed. So the flush is like similar as in the LevelDB. And it will be after flushed to the level 0, to our single level. Well, all the data that are stored, as I said, will be indexed by our B+3, which is stored in the persistent memory. So as I said, we only have a single level of sorted string table files. And for the compaction, we selectively pick some of the files there from our single level and merge them together and put them back to the level. Well, contributions that we've made are, first, a persistent mem table where we don't do any write-ahead logging, and it have stronger consistency compared to the LevelDB. We have our persistent B+3 index, which allows us to do a fast search for the data stored in the disk, and also it allows us to have only single disk component. And to do our compaction, we have our selective compaction with our 3 schemes. And one of our schemes is for the garbage collection, and 2 other schemes are for the increasing sequentiality. So let's go over the first contribution, and that's a persistent mem table. Well, as in the LevelDB, we use a skip list. However, in the skip list, we guarantee only for the consistency, only for the base level of the skip list, because the main data, the key value pairs are stored there. And the upper levels, the link levels, we don't guarantee, because if the crash happens, we can always recover those. How we ensure the consistency of insert to the mem table, that as follows. So we need to insert a key value pair. So we create a node with a key value pair. We make the next pointer to the needed node, and we CL flush it to the persistent memory. After that, we atomically change from the needed node to our newly created node, the atomically next pointer. This way, we achieve a very strong consistency. And now let me talk about flush operation and how we do it. So during flushing of immutable mem table to the disk, we do our k index insertion to B+3. And as for the B+3 implementation, we use fast and fair B+3 that was introduced in the previous year's FAST. For the flush, we use 2 threads, file creation thread and B+3 insertion thread. So we do a flush of the immutable mem table, and we create a file, right? While creating a file, we create indexes of that file for each key value pair. After saving it to the file system, we send that list of indexes to our B+3 insertion thread. After B+3 insertion thread is done, we after verify all the changes, saving all the metadata to the manifest file. Saving by it, we verify that the flush operation is finished. Now let's explain me about the compaction operation. So why we need a compaction operation in the first case? So let's imagine we have these 3 files, and all the key value pairs are valid inside of those files. And if new files comes up with some of the duplicating key value pairs and some of the key value pairs from the older files get obsolete, right? Well, we can tolerate some of the garbage if it's small in those files. But however, if new files comes up and too many key value pairs in those older files get obsolete, then that's too many garbage, and we want to, for example, merge those 2 files together. So basically, we need garbage collection. And the second reason why we need it, as for instance, if the application issues a range query, for example, here from 5 to 12, and these are the files. So if they are stored stores key value pairs quite bizarrely, so it might need to search few of the files to retrieve all the key value pairs to return it to the user. So we need to improve some of the sequentiality, so to do less of the random read. So we introduce selective compaction, and what it does is select some of the SS table files and mark those files as a compaction candidates. We preserve our compaction candidate list, and from those compaction candidate lists, we pick most overlapping files and merge them together. To select those compaction candidates, we have, as I said before, 3 of our schemes. Live key ratio selection of an SS table, that's for garbage collection. Leaf node scan in the B+ tree for sequentiality. And degree of sequentiality per range queries, that's also for sequentiality. Last 2, please look in the paper for the details, and I'll be explaining just the first one. So let's imagine that we have our persistent mem table, and we have our list of 3 files. So we preserve for each file, we have for each file the live to total key ratio. As you can see, they're below of each file. So the red one is like absolute key value pairs, and green one is valid key value pair. So if we have if that ratio drops below our configured threshold, then we mark that file as a compaction candidate. So if if the new file gets flushed and it's switch this the key value pairs to the new one. In older files, some of the key value pairs gets obsolete. So for the file 2, the ratio becomes 0, and we can just simply delete it. But for the file 3, there's still some of the valid key value pairs. That one we mark as a compaction candidate and put it to the list to be compacted later. This way, we pick some of the compaction candidates. So after we mark some of the SS table files as a compaction candidates, we do compaction. So let's imagine that we have a file from file 0 to file 4 as a compaction candidates. And as a flush operation, we use 2 threads for the compaction. So first, we pick the most overlapping files in those candidate files. So that files is like, for example, file number 1, 2, and 3. And we start our merge operation. So we merge, we create our first file. While creating our first file, as in the flush, we create our index list for that file. That index file is sent to the B+3 insertion thread. while B+3 insertion thread does its insertion, concurrently, file creation thread does continue the merging and creates a second file. Well, it goes on until the last file does finish up with inserting the indexes to the B+3. After it's done, we save all the metadata to the manifest file. After saving it to the manifest file, we validate that compaction procedure is finished. Well, let me go over the general operations. First one, it's a put operation of the key value pair. So it's simply first, it's key value pair inserted to the mem table. When mem table gets full, those key value pairs go to immutable mem table, and after they go to the disk, and B+3 indexes to those key value pairs. And we have a special operation called put if k exists, if not exist, with a statement. It's, we needed those operations as, for example, the update operation. It's the same as put if key exists, right? So it's very, there's quite an application that needs such operations. So first what we need that, we need to verify that the statement is fulfilled and it's true. So we query first with the mem table, which is more priority. After we go to the immutable mem table if its mem table is false. And if the immutable mem table returns false, then we go check B+3. If that one returns true, after that only we put our key value pair. For the get operation, we need to first query the mem table because our freshest key value pairs are stored in the mem table. If the key does not exist there, we query the immutable mem table. If it also does not exist, we query the B+3 and we return those value from the disk. For the scan operation, if a client tries to scan from ki to kj, we create an iterator for the mem table, immutable mem table, and B+3 index. So priority goes first for the mem table value, and after for the immutable mem table value, and after for the B+3 iterator value, which returns the value from the disk. And it goes until the last key in there. So let me start with the evaluation, and we used Xeon processors. Our DRAM was configured to be 4 GB, and we emulated our persistent memory to be 7 GB. Most of we used for our storage an SSD. DB, for evaluation, we used DB size of 8 GB and 20 GB. However, for this presentation, I'll be showing only results of 8 GB. We configured mem table size for the both of LevelDB and for ours in the evaluation to be 64 MB. For the emulation of the persistent mem table, we emulated of write latency to be 500 nanoseconds. We made read latency and the bandwidth of the persistent memory same as a DRAM. To control the persistent memory pool, we used Intel's PMDK. Let me start with a microbenchmark of the Google DBbench. And let me start from the first one of the random write. So all of the results are basically normalized throughput to the LevelDB. So basically LevelDB's results will be at 1. Throughput unit is kilo operations per second. And we evaluated our work for the value size of 1 kilobyte, 4, 16, and 64 kilobytes. So we can see that it has a pattern of increasing performance with increasing of value sizes. For the random breed operations, it has a not really great performance gain compared to the LevelDB for the case of 1 kilobyte due to the low locating overhead. And for the 64 kilobyte of value size, it's the overhead amortizes due to the large value size. For the range query evaluation, we used range size of the 100 keys. And only here, we have a poorer performance compared to the LevelDB due to our low sequentiality of kilobars stored in the disk. But overall, SLM-DB managed to have, on average, for these benchmarks, 2.5 times less disk write amplification. And in the worst case, it used up to 700 megabytes of persistent memory. So let me go over for the sensitivity. We used for the sensitivity DB bench. So first one is write latency sensitivity. And we emulated write latency by inserting CPU pulse after CL flush. And from this result, we can see that even for the worst case of our scenario of persistent memory having write latency 900 nanoseconds, it still performs better than LevelDB. And for persistent memory bandwidth, we emulated by using thermal throttling. So we emulated our persistent memory in the second socket, and we thermal throttled that socket. And we can see that our performance does not fluctuate much. For the YCSB performance, so here for the load workloads, it performs even better than in the DB bench for the insertion. For the workload E, it performs really great. And it consists of 50% of read and 50% of update operations, and performs greatly due to we have a really nice update operation to do. So, and for the workload E, which consists of mostly of scan operations, it performs poorly only in 1 kilobyte case. But in overall, it performs really great. And it has up to 7.7 less disk amplification. So let me conclude this. So we introduced our novel design for key value store with persistent memory, which has a better write and read performance compared to LevelDB. That has a comparable scan performance, lower write amplification, and near optimal read performance. That's it. Thank you, everybody. Any questions from the audience will be welcome.
All right. Thank you. Any questions? So, oh man, many questions. Oh no, I have a question too. All right, but maybe you can go first.
Okay. Hi. So, do you have any idea of what fraction of the benefits come from having a single level in the disk versus from having the skip list be in VM?
Can you elaborate?
So, for example, if you have a single level on disk in traditional LSMs, how much of the benefit do you get just from that?
So our benefit of having just single level disk component is that we do less merge operation. Due to that, we have a less disk write amplification. So our compaction does selectively pick some of the files from that file and merge them together and put it back to the level.
And that would carry over to conventional LSMs as well, right?
I'm not sure about that. Maybe we can discuss about it later.
Thanks.
Yeah, you asked the question I wanted to ask. So I had maybe I'll just ask my question right now. So my question was more like the other way. Look, if you just did move the mem table to persistent memory and didn't do anything else, do you have any numbers about how much speed up you would get just from that?
Oh yeah, sure. So I have a slide for that, backup. So here, so we have as you can see, LevelDB plus PM. That one is at having a persistent mem table inside of the LevelDB. So as you can see, the So it's normalized by the latency. So it have a performance gain only if it has a large value sizes. Also, it has a performance performs better for the having less disk amplification because it doesn't need any logging, right? In the second graph.
This is Chen from Huawei Technologies. My question is, now you have two places that you're storing your metadata. One is in the B+ tree, the other one is already in the SS table.
Can you speak louder, please?
Sure. You have two duplicates of metadata. One is in the B+ tree, persistent B+ tree. The other one is already in the SS table of each SS table, right? And this redundant metadata. B+3 stores each key value pairs that's stored in the disk, and the metadata that's stored in the manifest are like actually the ranges of SS tables. It doesn't store like each key value pairs that's stored in each file. So what I'm talking about, not the manifest, it's the SS tables index block.
Oh, that's true. I mean, yeah, we wanted in our implementation was on top of the LevelDB. We actually wanted to get rid of that. However, we needed that for the compaction because
that's my point.
Yeah. I mean, in the future work, we would like to optimize it and get rid of it and make the compact.
It's not easy to get rid of the index block of the SS table.
No, we didn't get rid of it.
Even if you want to do it future, it's not easy.
Yeah, I know. So that's why we didn't do that in this work.
Okay. The second question is regarding the SS LevelDB's design, because other than the level 0, all the level below has non-overlapping keys. The SS table in level 1 and level 2, they don't have overlapping keys.
No, well, yes, I didn't clearly say that, but in level 0, the SS tables do overlap.
I'm saying level 1 and level 2, they don't have overlapping
Oh,
keys.
yes, they don't have overlap.
Then by removing this to a single level, you essentially have level 2. Basically, it's going to be very big. But now you have, because your way of doing single level is essentially doing the GC.
Yes.
Then that means the new blocks you're writing going to have the overlapping keys, and it's not strictly sorted.
Oh yes. Yeah. That's why we have like our 3 schemes, right? As I said. But I talked only about the garbage collection scheme. But there's 2 other schemes that increases the sequentiality. I mean, it doesn't do total sequential order, but preserves some of the level of it, and you can see it in the paper. And
but that also introduces more right amplifications, because if you're trying to make that sequential, you need to move data more.
Yes. I mean, for that, I mean, we have some of the parameters to thresholds whether to decide whether we need those like SS tables to be merged or not.
Okay.
Maybe you can take this. Maybe you can take the rest of this offline.
Okay.
All right, let's thank our speaker.
Okay. Thank you, everybody.